Hello and welcome to this PIANC webinar on salt intrusion in inland waterways. My name is Tom Amani and I was the chair of this working group, and I will be leading you through, together with my working group colleagues, through the webinar today. Let's get started with the introduction. So this is our agenda for today. You will have seen this on the registration page. We have two parts. First part presented by the working group itself, where through a number of presentations, we will give a short summary of what's in the report. And in the second part, we will have two external speakers from outside the working group who will reflect on the report and give us their insights into salt intrusion in inland waterways. At the end of each part, we'll have a Q&A session. So if you have questions, please put them in the chat and we will get to them at the end of each part. Firstly, a little bit about the working group itself and who we are. This is the group. I won't give you all their names, but we are a group made up of professionals from around the world, different countries, China, the Netherlands, Belgium, France, Panama, Germany, and Spain, and the US. We started the working group in 2017. In June, and the report was published earlier this year in the summer. So it was 4 years in the making, and during that period we had meetings hosted by members of the group in Brussels, in Seville in Spain, in Panama City, in Belgium, St. Niklaas near Antwerp, in Grenoble in France, and in Hamburg in Germany. Of course, because of the pandemic, our last meetings were all virtual. So since the meeting in Hamburg, beginning of 2020, we've finished off all virtually. And this presentation here is virtual as well. Okay, so the contents of the report and also of our webinar summarized here. The report starts with general aspects of salt intrusion. Why is it something that's worth studying and worth taking into account in navigation infrastructure projects? After that, we have a chapter talking about what causes it, what are the mechanisms of saltwater intrusion, what mechanisms have an effect on it. And after that, we have 3 chapters, which are also then the following 3 presentations in this webinar. A chapter on measuring and monitoring saltwater intrusion, a chapter on mitigating it, and also a chapter on modeling it. That's numerical models and physical models. A little bit about what this report means in terms of updating the existing literature. Now, there was a PIANC report from the 90s, 40 pages long, and very summary of the sorts of issues which have come across. Since the 1990s, there have been a lot of projects, like the expansion of the Panama Canal, like the deepening of the Elbe and the new Rotterdam Waterway, and building of new, larger locks, which have given engineers in the world a lot of new insights into how to study this phenomenon and also how to mitigate it. So it was a good time for an update, and our update is here on the right, our PIANC report, which in 140 pages long. We thought that was not long enough, but we needed to be concise as possible. But we think that it's a good update on what was available before. And now I'm going to hand over to my colleague Frank to tell you a bit more about the mechanisms of salt intrusion, why is it important, and what affects it. Over to you, Frank.
Thank you, Tom. My name is Frank Kösters, and I will carry on from here. First, let me point out that the report is called Salt Intrusion in Inland Waterways, but keep in mind that inland waterways, they comprise tidally influenced estuaries as well. Therefore, we have to look at estuaries. We have to, like the Elbe estuary on the map on the right-hand side, shown as a B. Then we have to look at canals with dams, something like the Panama Canal, and locks, like the Lake Isle, shown on the right-hand side map with an A. These In all these areas, salt intrusion can appear, and it is pretty important as it influences the availability of fresh water with many stakeholders possible for water use, such as agriculture or nature conservation, industry, or potable water. Within the report, we give study methods and mitigation measures for these phenomena. For tides for estuaries, or the salt intrusion in estuaries, the salt intrusion itself, it's depending on the freshwater discharge, so the freshwater which just pushes the salt out of the estuary, and the influence of tides, and the relative strength of the freshwater discharge and the tides, they define the different ways salt water is intruding into the estuary. If you have relatively small tidal range, you get a stratified situation shown on the top panel on the figure here, where a salt wedge is developing, and we have stratified conditions. With very energetic estuaries, you get fully mixed conditions, and there is a front which develops between the freshwater and the salty water from the sea. It's on the lower graph shown as fully mixed. And then there is a situation in between where we have intermediate tidal energy, and you get partially mixed conditions where you have only stratification during some part of the tides. However, all these might change if you take into account effects such as changing sea level due to climate change, or the impact of human interventions, as an example. But it's not only tides and freshwaters, but also other physical mechanisms which may play a role in salt intrusion. Here is an example of a typhoon in the South China Sea, shown on the right-hand side, with two different typhoons with different tracks. And what is now the impact of a typhoon on salt intrusion? Well, on the one hand, during the typhoon itself, precipitation is increasing. Therefore, the surface salinity in the adjacent sea is decreasing, and you get less salt outside on the one hand. On the other hand, during the typhoon, evaporation is increasing. You get uplift of the halocline in the coastal sea, and you get increased mixing. Therefore, the salinity is increasing. As you can see, that's a very soft or a very complicated mechanism which play a role, and we are going into that within the report, and typhoons are just some examples of extreme weather events which may play a role. On the other hand, we get salt intrusion through locks, and there are three main mechanisms involved in that. Firstly, there's the effect just due to the through the boat itself. You get a volumetric displacement, which is when the boat is leaving the chamber to the sea. It results in a flow from the sea into the lock chamber, and when it enters into the adjacent canal, for example, the salt water is going out into the river, and is carrying salt during that process. A second mechanism playing a role here is the so-called lock exchange, which is a density-driven current. When salt water flows from the sea underneath the fresh water due to the difference of density, it is mixed into the lock chamber and then goes into the canal as well, with a bigger difference in salinity, producing a bigger difference in density and a faster density current. And finally, you get something like a lockage prism, where you have, when you have different water levels, for example, at high tide, the water level difference between sea and canal is leveled, and the lock chamber using sea water, which is then emptied onto the canal when the lock is leveled at the inner gate. In order to visualize these processes a little bit better, you can see here on the animation boat coming in from the canal, being in freshwater, and then when the upper gate is open and the boat enters the lock, you see on the bottom the saltwater intrusion due to the density current in the canal. And then once the boat is leveled down to leave to the sea, you see the salt coming in from the sea into the lock chamber when the lower gate is opened, and the density current with the salt intrusion entering the lock chamber. And it works as well vice versa. When the boat is coming up from sea and is leveled up to leave into the canal, you can see here the salt intrusion again when the upper gate is opened, and together with the boat, the salt water is leaving into the canal. Well, that is a very, very brief overview about the mechanisms we can show here. To dive deeper into it, you have to look into the report. And from here, I'd like to hand over to Tom again.
Okay, thank you, Frank. So that was our introduction. Salt intrusion in inland waterways is a topic which is often needed to be taken into account in navigation projects, the deepening of a waterway or the building of a new lock, for instance. And these are the things that can have an effect on it. For the next presentation, we're talking about how do you measure salt intrusion and what sort of measuring campaigns you would need to do to study it for your navigation project. And to present that, Gary Brown from the US will take over. Off you go, Gary.
Thank you, Tom. I'm going to be speaking about measuring and monitoring of salinity and some of the things that questions you may want to ask yourself when you're trying to develop a means to measure and monitor salinity. The chapter is laid out basically as a guide to develop sort of the set of questions you would want to ask yourself when you're trying to understand and design a salinity measurement campaign. And the reasons for that is because there are a lot of different uses for salinity measurement that everything from modeling to just monitoring or informing decisions. But as a general rule, the salinity measurement can be an expensive proposition because of mobilization costs and equipment costs. And so you want to target the salinity measurement to optimize it for the problem that you're looking at. And this chapter is written really as a way to bound the problem, to ask yourself all the questions that you need to ask yourself in order to properly design a salinity measurement campaign. And so that's the thinking behind it. We have sort of a question, it's kind of a wordy question here, but the way we phrased it sort of that way at the bottom of this: what's the least cost alternative that will provide sufficient quality controlled information to inform decisions that address the specific saltwater intrusion concerns associated with a given lock, lake, river, or estuary? So it's just a long way of saying the same thing. How do we optimize what are almost always limited resources to get the data that we need for the problem that we're looking at? And so there are several questions that we first ask ourselves. The first one is, of course, what specifically is the problem that we're interested in? There are lots of different problems. Is it something that's what's the mechanism of the saltwater intrusion? Are there one or multiple sources of salinity that are in the area? Is the problem we're interested in something that is a short-term problem or chronic problem, or is it an acute problem, or is it a chronic problem? Is it something that's more gradual? Is there spatial coverage, or is it a local problem? All of those, and even referencing the actual mechanism of intrusion as well is important, because all of those things will help you guide your decision making about what type of data you need in order to understand the problem that you're addressing. Excuse me. Okay, so then once you establish that, it's important to develop a detailed plan before you execute this plan on exactly how you're going to collect these data. You certainly want a robust budget, robust and realistic budget estimate for yourself. You want to make sure you have a plan to collect metadata so that you record everything about where and when you collect the data. In this sense, it's very similar to data collection in a laboratory, in the sense of making sure that you've documented everything that you have, and not only for your own project, but also a recognition that you'd like to be able to archive this data and possibly use it later, since you're investing in it, and you want to be able to have all the data available so that someone can pull it out and use it, or that it can be published on the web for more general use. You want to develop a systematic and strict and consistent procedures for the data collection to make sure that if you are deploying multiple instruments or and you have multiple individuals deploying it, that they're all deploying and recording in a fashion that is consistent across the data collection methods, and that you develop methods that are consistent with the design of the equipment that you're using, that satisfy the design constraints for that equipment. And also, you want to develop contingency plans in case, because there's always something goes wrong in data collection. You lose some equipment, equipment is damaged. How do you mitigate for that so that you don't have that you deploy all these data and you lose a few? If you lose a few data collection points, you don't have enough data to sufficiently inform your project. All those things should go into the data collection plan. We talk about means of measuring salinity. Of course, there are several means to measure salinity. Two of the most common are basically bottle samplers that get actually discrete samples of water that is then sampled for salinity, and then also in situ conductivity, temperature, and depth sensors that in real time measure those parameters in the water, and you can deploy them and retrieve them and get those are giving you much more frequent and continuous observations. And we talk about the advantages and disadvantages of these. There are cost advantages, there are maintenance advantages and disadvantages, and which method you select is going to be very dependent on the type of data that are necessary for the problem that you want to address. As an example, you can get broader and longer term coverage with bottle samplers, but the frequency and time is much less. So if you need higher frequency measurements, you may need to deploy CTDs in order to get those. So those are the types of things that you want to address. And then also you want to look if you're going going to have a measurement campaign. There are two of the primary types of campaigns that you can deploy are either sort of synoptic station measuring campaigns where you have stations where you're collecting data continuously, or you have intensive campaigns on boat-based campaigns where you're collecting possibly ADCP together with salinity to get sediment fluxes across inlets, or things like that, where you have much more intensive data collection. And which methods you use, again, are going to be dependent on the project that you're engaged in. And so the first questions that we ask at the beginning in order to organize it help inform these types of questions. So again, these chapters really just as a way, hopefully, to help you organize your data collection campaign and get the most out of your funds. And we hope that it's helpful for you in terms of helping you understand and collect data for salinity intrusion. So thank you very much. And I'm going to return it to you, Tom. Thank you.
Okay, thanks, Gary. before I move on to the next presentation, which will be about mitigation, I want to say that you can put if you have any questions for the speakers as you go, you can put them into the chat now, and we'll get to them at the end of the part one. But you can put them in the chat now, and then we'll address them later on with the speakers. The next presentation is about mitigation. Yeah. So if your navigational project is going to produce salt intrusion, which by particular stakeholders in the region is considered to be not acceptable, and you have to do something about that, one of the options is to mitigate the salt intrusion. And in the report, the biggest chapter in the report is actually the chapter on mitigation. So there's a lot of things in the report, a lot of options that we talk through, and also give advice at the end of which ones are perhaps most appropriate for particular situations, and also ones which have been proven in the past decades to work. I think our emphasis is really on which ones have been proven to work. But we split the mitigation chapter up into mitigation in estuaries. Yeah, Frank at the beginning in the introduction talked about how inland waterways are split up in our report into estuaries and closed canals with locks, and we split the mitigation chapter also in mitigation of salt intrusion in estuaries and mitigation of salt intrusion through locks. We also have a section on mitigation in the groundwater, but our experience is that groundwater is not necessarily an important factor in inland waterway projects and navigation projects, and so it has less emphasis, but it's still important to think about whether or not it has an effect in your case. But in this presentation, I talk about the mitigation in estuaries and locks. Just a summary of a few of the examples that we show in the report. Here we have a couple of the examples that we show for salt intrusion into estuaries. On the left, we have a so-called saltwater barrier. This is an example that's used in the report, where you have it's like a sort of a barrage or a weir with gates that close when the salt water appears to be traveling too far upstream. So you can stop the salt water here by closing the gates. But in other conditions, other times of the year when there's enough river discharge, then you can open the gates, or maybe even there's flow over the entire width of the river in those situations. But for the drought periods where it looks like the salt water is coming too far upstream, then you can have a structure like this, which closes the gates. Similarly, on the right, we have an example which will be talked about also later by one of the external speakers, by Bill McAnally, is the salt barrier in the Mississippi. And this is a mitigation measure which is a temporary measure. So it's a temporary salt barrier which is built only in the periods of drought, and that's something where they down in the Mississippi River, they have decades of experience in putting this in when it's necessary. There's more information on that in the report. Another mitigation strategy which is talked about in estuaries is adding mixing. And here I'll explain a little bit about how that works. Imagine this is your situation. You've got the river coming from the right, flowing from right to left. The sea is on your left, and you have here the dotted lines or the dashed lines are your isosurfaces of constant density. So here you can see that partially stratified or stratified situation with the salt wedge, the heavier salt water intruding farther upstream. Here, this is the situation, and this red point here is your point of maximum intrusion, right? Depending on how you define it. So then, what you'd want to do is with this mixing mitigation measure is you add some sort of intervention in here to induce mixing in the water column. Now we talk about a couple of intervention types. Creating lateral flow, bubble screens or bubble plumes, pumping boats, or strategic dredging. These are described in the report. The effect that it has on your density profile is shown on the right. You have a much more vertically mixed system, so the lines of constant density are much more vertical, and this has the effect of moving your point of maximum intrusion from the point upstream where it was to be a little bit farther towards the sea. So in this instance, you've reduced the salt intrusion. Of course, if you're actually, the reason why you want to reduce salt intrusion is because you use it for something, and where you use it, you extract it from the surface water. This measure may actually be counterproductive because you've increased the salt concentration near the surface in some places. So you always have to be careful about making interferences in your estuary. For locks, there are a lot of different mitigation measure types. That's a large part of the report here. I'm going to talk about only a couple of them. The easiest one, I think of it as the easiest one, is closing the gate quickly. In this picture, you have on the x-axis, you have time, so the time that your gate is open for the ships to enter and exit, and on the y-axis, you have the amount of this lock chamber which has been exchanged. So if your lock chamber was salt, then at 100%, all that salt from the lock chamber has gone into your canal, and that is 100% salt intrusion. And here we have two instances. If you close the gate at 30 minutes or at 20 minutes, then you can see that the amount of salt intrusion has dropped from, what is that, 85% to 70%. So closing the gate earlier, that's a very easy measure. And I remember when I was young, my grandfather always used to tell me that I needed to close the door to keep the cold out because he wanted to keep the room warm, and it was only polite to close the door behind you. So that's the same sort of principle here. You've got to close the door behind you to keep the salt out. Another couple of measures is putting higher sills at your lock heads. This could be detrimental for shipping because it reduces possibly your underkill clearance of your vessels. But here on the picture at the top here, you see three different numerical simulations of salt intrusion for different heights, and you can see that the larger the sill, which is run 3 here, the slower the exchange. So the sill has the effect of not only reducing the height over which exchange happens, but also reducing the speed, because the speed of lock exchange is proportional to the square root of the height. So a smaller height of the exchange column, the slower the exchange. And underneath, we have examples of where you can simultaneously flush the lock chamber with fresh water to stop the salt water from advancing. And the lower picture has got 3 different velocities of flushing. So you can see that here the salt water is prevented from moving beyond the lock. Another system which we describe in the report as possibly the most effective system at really reducing salt intrusion to almost nothing is the so-called Dunkirk system of saltwater substitution. These pictures are from a lock in the Netherlands, actually, which is a slight change on the Dunkirk system. But this involves a completely integrated leveling system in your lock and a lot of different culverts. You can see on the top right of these 3 pictures them building the culvert systems in the 70s and 80s. And that's got a very, very large cost in building it, and it takes up a lot of room as well, because you have these receiving basins which store fresh and salt water during the process. The process is described in detail in the report. This one is the most effective one at reducing salt intrusion to almost nothing, but it costs a lot of money to build, and it also costs a lot of time for ships to pass it, because they have to wait quite a long time in the lock while the salt water is extracted. So these are the sorts of examples we have in the report. Many more examples as well, and at the end we also have a table to summarize which ones we think are the best ones and in which situations they're the most useful. Okay, so that's mitigation, and now the final presentation for today and the last chapter is modeling, physical modeling and numerical modeling, and for that I'd like to pass over to Tom van der Wekke. Off you go, Tom.
Thank you, Tom. Well, I like to present a few slides about modeling, as we have seen in the mitigation contribution, but also in the measuring and monitoring contribution, it is necessary to develop those measures or those mitigation measures, and therefore we need some tools to compute whether those mitigation measures will help, yes or no, and in how far they will help. So therefore, modeling is very often used to get a qualitative but also a quantitative impression of the rate in which measurements can be carried out, in what kind of shape the mitigation measures are needed. So that's important, but more important is even that the salt intrusion in inland waterways can hamper many freshwater related interests, and governments ask more and more for detailed studies to assess the impact of changes in salt intrusion. Instances, the deepening of the Elbe River or the Rotterdam Waterway recently, Loire and the Seine in France, the new Panama locks, new sea lock IJmuiden. Salt intrusion, as we have seen in the contribution of Frank, is a very complex physical phenomenon, and there are no simple approaches to determine and quantify impact of works. So insight in the differences between present and future situation, or past and present, are necessary, and well, the only means that we have to get an impression is modeling, in fact. Of course, the knowledge of specialists is also important, but also they also need models to get more quantitative information. In the pre-computer era, we only had two tools, the physical models, the so-called scale models, or on the other hand, greatly simplified mathematical models. Nowadays, we are happy that we, besides of physical models, we also have a number of numerical models. So I like to tell a bit more in detail about the physical models, the advantages and the disadvantages. And physical models are, well, very complex and expensive to develop, to operate and to maintain. Interventions in the infrastructure, for instance, change of the bathymetry or geometry, requires new elements in a model. An important problem also is, well, what to do with the surplus of salinized water. In a scale model, we have real water. The seaside is salt water, the riverside is fresh water, they meet each other, and what we have in the end is a surplus of salinized water. But where to go with the salinized water? That is also a very large problem, or can be a big problem. On the other hand, physical models reflect very well the processes we like to investigate. And under one condition, we have the so-called laws of scale, and they have to be fulfilled. An important one is that in a scale model where everything is much smaller than in reality, also the turbulent processes that are very important for salt mixing and salt intrusion have to be reflected in a sufficient way. So scale models to be fulfilled are very important. Scale laws are very important to be fulfilled in scale models. Advantage is also that physical models are not only describing but also predicting. Two examples of physical models. At the left side of this slide, you see the so-called model Rijnmond in the Netherlands in the 80s and 90s of last century. It was a very big scale model of the so-called lower river area, with the North Sea at the left side and the upper river side at the right side. And the measure of the model was more than 100 meters from left to right. On the other hand, we see a more recent model of the Panama lock, where maybe a bit difficult to understand, but the upper picture gives a situation when the doors are just opening. So at the right side, we see the freshwater area. At the left side, we see the lock with salinized water. And when the doors open, you'll see the salt water coming from the loch in the fresh water to the right, and in the lower picture you see the under layer, the bottom layer with fresh water moving to the right. The simplified mathematical models have as properties that they are very easy to use, they are cheap, but on the other hand they are mainly describing and hardly predictive. They are time average, and they don't give a quantitative insight, it is only a quick qualitative insight. And then some characteristics of numerical models. Also, numerical models are complex and expensive to develop. On the other hand, they are cheap to operate and to maintain. They're also cheap to change the bathymetry or the geometry. Long-term evolutions can be costly because they need a lot of computing time. Therefore, we have different kinds of models: one-dimensional, two-dimensional vertical, two-dimensional horizontal, three-dimensional. They are all available presently. Seen many times that people like to choose for the most complex one, three-dimensional, but we have to be aware that it is not always necessary, and especially when you want to make long-term evolutions, 1D or 2D models can be much cheaper than the 3D ones. But as computer capacity in terms of memory and velocity is becoming a minor issue, the application of three-dimensional models is more and more common. However, not always necessary, and sometimes physical models are even preferred in cases that even a numerical model is not able to reflect the processes that we want to investigate sufficiently. Here at the right side, we see a picture of a 3D computation of the North Sea Canal in the Netherlands. What we see at the right side of the picture are the locks in IJmuiden. The right side is where the fresh water is coming in, and where there is hardly any mixing mechanisms in this canal. You see a very stratified situation with the salt water on the bottom and the more fresh water at the surface. Some other examples of the results of numerical models see on this slide. In the upper side, we see the Loire estuary in France. At the left side, we see a situation with neap tide, which means that the turbulence in the estuary is very low. So we see in the left upper corner picture, we see two situations, the surface layer and the bottom layer, and you'll see that the surface layer is relatively fresh and the bottom layer is relatively salt. At the right side, we see the same estuary, but at spring tide, so that means that we have a more turbulent situation, and to see that the difference between the upper layer and the bottom layer are much smaller than in the left picture. At the bottom side, we see a ship in a lock chamber, and at the left side, we see the lock door at the seaside, and the process of leveling the water level in the lock chamber and the seaside has just started. So we see the salt water coming in through the doors in the lock door. Just started. At the right side picture, we see the same process after several times. You see proceed the salt water wedge along the bottom of the lock chamber. So with that, I'm coming to my last slide, and well, I have to give a warning, so be aware that each model is simplifying reality. And well, sometimes in an ironic way, modelers are saying, well, the best model of a cat is a cat, and most preferably the cat itself. What we want to say is this: use of models requires specialist knowledge of, among others, the hydraulic processes, the salt intrusion processes, the properties of a model, and the numerics of a model. So when you are not a specialist yourself, always call for specialistic knowledge when you are using models, because when you don't do that, we let the model be a ventriloquist, and that is not what we want to do. Okay, thank you for your attention.
Okay, thank you, Tom. We've managed to give you, within the time stated on the agenda, a short summary of what's in the report via these 4 presentations. Obviously, there's much more detail available in the report. We had in the agenda time now for questions and answers to the members. After that, we'll have a short break and come back at the turn of the hour for some external speakers. Thus far in the chat, I've seen some questions about how to get hold of the report and how to become a PIANC member. But you also have the opportunity now and in the Q&A after the external speakers to make use of the expertise here at the working group. We've got 8 to 9 experts willing to give you free advice on your salt intrusion navigation project within the next 10 minutes. So make use of it if you want to. But of course, we can't take any responsibility for anything that happens with it. But so now's a good moment to put your questions into the chat. If you have questions which you want to ask us at the second Q&A, then please feel free to do that. But at the moment, I don't see any questions coming up. The presentations after the break will be from external speakers. We have a speaker from the Dutch government, Mainte Blaas. He is busy with water management in the Netherlands, and in particular the operational water management. He will talk about how the Netherlands is hoping to make also salt management a part of their daily operation of their water distribution within the Delta. After him, we'll hear from Bill McAnally, who has had a long career working for the US Army Corps in Mississippi, and who has done many studies on the temporary salt barrier in the Mississippi, which came along as one of the mitigation measures which you can use in estuaries. And he's also had a career as a professor at universities and as a private consultant. So he will also give a presentation on his experiences, his reflection on the report, and also on that salt barrier. Make a few points. Because I don't see any questions, I suggest we now take a break and convene again at the hour mark to start with part 2. Thank you for your attention so far, and see you again in about 18 minutes. Okay, welcome back to this webinar on salt intrusion in inland waterways from PIANC. This is part 2, where we have some external speakers from outside the working group to share their experiences on salt intrusion with us. But before I hand over to the first of those speakers, I'd like to say that during the break, we had a number of questions coming in via the chat. Some long questions that maybe took a bit of a while to type into the chat, which is why they didn't come up on our feed before I cut to the break. But we've seen those questions, and we'll get to them in the Q&A at the end of this part. So thanks for those questions. A good basis for a discussion later. But first, we'll continue with the agenda as it was published and go to our external speakers. The first of whom is Mainte Blaas from the Rijkswaterstaat in the Netherlands, the Ministry of Infrastructure and Water Management. So thank you, Mainte, over to you.
Thank you, Tom. Thank you, PIANC, for inviting me to, as an external, to give an introduction and a vision on how we do in the Netherlands and how it relates to the PIANC work and the report in particular. I changed the title of my slides and my presentation a little bit. It's a broader picture on how we manage the water and salt in the water in our inland waters, instead of just the information that I originally had in mind. Well, as Tom already said, I'm involved in the Ministry of Public Works in the department that is responsible for managing and developing the knowledge on how we to design and maintain our management of water in current days, but also in the future. And I will cover the entire spectrum actually from operational to tomorrow and the day after tomorrow in my talk in the coming 10 minutes. And as Rijkswaterstaat, we're responsible on behalf of the ministry for shipping, maintenance, road infrastructure, water infrastructure, but also water quality and water quantity and water safety. And that all interferes in how we have redesigned the Netherlands. Originally, the Netherlands looked a little bit like this, actually, as it still looks in the Biesbos area. But nowadays, it quite often looks more like this. It's a heavily engineered piece of a delta in Western Europe. And well, that does have an impact on how we deal with the water world in our national government. As you see, the Netherlands, the river delta, the Meuse River, the Rhine River, and the Scheldt River in particular, they flow in through this low-lying area, and fresh and salt water meet. But yes, it's a heavily engineered system. We built weirs to divert at low water the river water and steer it to particular areas. These particular areas, only a few of them are still open in direct connection to the sea, original like estuaries, but many others, they're more enclosed. It's like Lake IJssel, the central part, the upstream part of the Rhine in the western part of our country, and in the southwestern part of the country. These have originally been estuaries or in contact with estuaries, but have been dammed mostly because of water safety, actually reasons and policies, shortening your coastline. It's all making it cheaper and safer. But it has a drawback in that sense that you have strict and hard interfaces between fresher and salter water. And ironically, some of these freshwater areas have become strategic to us right now. So not only as an accident actually, but more and more we have to rely on these areas for fresh water. And I'll go into that in my next slides. On top of, or at least at the bottom of everything, I should say, this delta is a sandy, clayey, peaty area where there's a lot of also internal salinization of groundwater seeping into our reservoirs. It is also something to be managed and being get rid of if we have the water to do so. So yes, how do we do, and what all kind of functions depend on the fresh water that we have? About half of the drinking water in the Netherlands is produced from free surface water, which is in the west mostly, and hence influenced by salt intrusion. At the same time, this inland water system is very important for inland shipping. These are the shipping classes and the way they connect, but also this is obviously related to where we make locks and where we keep things open, where we have to manage our locks. And also when river discharges get low, and they tend to get lower when changes due to climate change in the Rhine catchment, for example, take place. And summer conditions lead us to well, water shortages or scarcity, at least of water, like the picture you see in the right, really low discharges. We really have to be careful in how we divert our water, how we treat our, what we do with our water, because actually the Netherlands, we don't have an area somewhere where we can really make a huge storage. Even the storage that we do have in the groundwater is not sufficient to overcome a long period of drought. And you really then see that your groundwater reservoirs, they decrease and they require a lot of time to recover. So we need measures to be, well, careful and wise with the water. Currently, when it really becomes tough, we have a priority sequencing. It's also being referred to in the report. And this priority sequencing, this does refer to, well, some functions will get a longer and longer access to water than other functions. But of course, you want to avoid this sort of situation. So the whole challenge for the Netherlands is to become very smart and prudent with how we manage our waters. And actually, salt intrusion is then one of the big issues that's kind of limiting the quality and quantity of our water. Because how do we manage salt? We flush it mostly through the basins. We apply withdrawal measures where applicable on dams and locks. And some places we have barriers like bubble screens and sills to mitigate intrusion locally. But still, it all requires at least some amount of fresh water to function. All these mitigation measures also require fresh water, which is scarce. So we really should optimize this sort of water usage to maintain the salt-freshwater balance. And hence, our management really relies on an extensive observation network. Here you see an example of the salinity measurements in our national observing network in our water system. There's also water quantity measures, of course, like discharges and water levels. And this is published online. It's in a real live database. We extract it from our network every 10 minutes. It's being updated online. And this is available not only for the general audience, but the same information is available for our operators. Operators that do have to take decisions on an hourly basis or even a shorter basis to manage logs or weirs, for example. One example of a log being in construction in the Ghent-Terneuzen canal is that to optimize this log operation with regard to water quantity, water quality, and shipping is to build a decision tree and put it into a decision support system. This is just an example how this is being structured, but you see this relies very much on good information to make the decisions on a real-time basis. And what we do have for all our strategic areas within the Netherlands for water management is interpreted data. It's already put into information. It's put into contact through a dashboard system that we have for all our zones that contain chlorosity data, but also other information about water management. So this is how we do today, actually. And it's already quite sophisticated, if I may say, but we are even more ambitious because it can be done smarter. And not only to be smart, but also to become more resilient for future changes. And this is really called SMART or SLIM in Dutch water management. It's a matter of cooperation beyond the limits of, say, a main water body. It's involving upstream water boards, local government agencies that also manage part of the system, which is interconnected in reality. And by exploiting the interconnections and the way the whole system works, you can make more cost-effective measures for managing groundwater. For example, in this in the Rhine Delta area, it is at certain times beneficial to divert a bit of the fresh water upstream where it's fresher through bypasses, through the local network upstream into what's called the Hollandse IJssel branch. Have this solution in place requires not only a lot of tuning within the local authorities, but it also requires a good piece of information. And we're building now still in the development stage information screens that do have a lot of interpreted information of different networks combined. It relies on forecasting or predictions on the trends in the system, and it can be used along with a line of reasoning what measure to take when and with whom. And this is, well, it's putting an important basis for a future water management, actually. How do you design such measures? It's not easy, actually. It's a quite ambitious task. And as already the previous speaker said, data, observational data, and models are key to this. We invest a lot in complex 3D models, but also, as Tom said, simpler models to corroborate and to underpin how we design the management of these complex systems. And nowadays, these models are really capable of exhibiting the proper scales of variation that are relevant for the water management. This is an example of a cross-section in the Rotterdam Waterway in a currently freshly developed 3D new version of this area, where you see by the dots the observations at a certain moment in time, and in the color shades the model solution to the salt wedge in the estuary. And it's really, well, I'm a modeler myself. I see this is the better than that you hardly can get currently. But it's not only about being able to capture a certain instance, but also to being able to capture certain dynamics that are relevant for the way you manage the system. On the left here, this is a Hofmüller diagram, vertical in time, horizontal in space, of this Hollandse IJssel system. On the left, you see it observed. On the right, you see the same 3D model And you see this already reproducing the response of an extra flushing upstream and how the salt wedge is responding to this flushing over a dry summer, the dry summer of 2018. And this is putting a lot of confidence in the way we even further can fine-tune these sort of measures. And then, as if it's not enough, I think we have learned from 2018 as Rijkswaterstaat and local water boards that we can manage the water smartly, regionally. And this has put a basis on a higher level to repeat this template at a national level. The areas here highlighted are strategic of importance in the freshwater reservoirs. They are managed dynamically, but there's even a supranational interconnection between them. And you can depict this in the sort of scheme on the right. And this is the blueprint of what we're currently developing to become more resilient to climate change in the future. It's a more resilient way of making optimal use of the scarce water that flows in. When there's no rain for a month or longer, we fully depend on the water that's coming from abroad. We anticipate so we can buffer locally, and we anticipate also on weather and forecasts, and we do it smartly. So we adjust and fine tune the measures that are required. And of course, we can only be smart and be clever with the water that we do have. So there's also complementary measures on how to use the water, which function to place where, etc., etc. So there's a whole program. It's within the national strategy, the Delta program, to keep this in balance for the future. And then we're confident to be prepared for at least the coming decades to be resilient to climate change, for example, and provide sufficient water for all our functions in the Netherlands. Still, extreme sea level rise and extreme climate change may put another stress on this sort of systems. So at the same time that we're actually having developed this strategy and start to implement it, we're already stress testing to what degree this can withstand extreme climate change, extreme sea level. And that's a separate piece of work, separate programs. We do that sort of work. So to wrap up, water and salt intrusion management, it's a balancing act. It's a balance between fresh and salt, but it's also a balance of different interests, of course. And I think at the object level, where you start to redesign or you implement an object, a structure in your system, you have to already commit to certain operational design requirements that sometimes can be conflicting. I think when you take it to the next level, it's on a regional scales where we have hard and soft objectives that we try to keep in the air as much as possible. And on our national level, the story repeats, where we now see this coupled system of buffers and changing requirements locally, regionally, but also over time to keep up in the air. It's all about, and that's the original title of my talk, also how you use the data as a basis of what you know, put it into information, put it into knowledge, and in effect, in underpinning of decisions and design. So the better your insights, and also something that PIANC is providing, the better your decisions, the lower your risk. In that sense, engineering, classical engineering is evolving more and more to a different sort of engineering, more integral, more adaptive, and that's complex. But I think it requires a lot of knowledge, but I see that we're capable of doing it, I think also internationally. So last but not least, the future becomes more demanding. I think adjustable strategies, those are the key to be flexible for future changes. Thank you.
Okay, thank you, Mainte, for your presentation and a look to the future, but also the present. You mentioned climate change and the challenges that is giving to water management in the measurement. That hasn't been an emphasis of our presentations from the working group earlier, but it is mentioned in the report that this is becoming an increasing driver of the questions that engineers get about salt intrusion in inland waterways. It's not just a navigation project, a new navigation project, which is driving the need for studies into saltwater intrusion, but just a study of the existing system under pressure from climate change. That's something that's definitely covered in the report, and you see from Mainte that there are governments out there and people out there that want to to know the answers. Okay, if you have questions for Mainte, then you can put them in the chat. We'll address them in the general Q&A at the end. So for now, I'd like to move on to our next external speaker, Bill McAnally from the US, with a long career at the US Army Corps in Mississippi and as a professor and private consultant. He's going to talk about his experiences there and also his reflections on his career and on our report. So over to you, Bill.
Thanks, Tom. First, my congratulations to the working group for a really excellent document putting together on saltwater intrusion. And I'd like to just call your attention to a few points that particularly struck me in the report. The first is on page 82 of the document, and it says this: numerical models right now have an ability to predict with accuracy the response of hydrodynamic systems, hydro systems, but there's a limit to that, and that's due to two things. One is limitations of the models themselves, but which are getting better all the time. And as Tom has mentioned, it's due to they're getting better. They're quite good, but it's also due to the fact that we don't understand completely the physical processes that are involved. And the examples of that are the reasons for that is that salinity intrusion over small increments and over simple changes can be almost linear, and we get fooled by that. And so we can use simple methods and even sometimes mildly inaccurate models to make predictions because it's almost linear until suddenly it isn't. And the best example of nonlinearity in the report is on page 20, in which it shows that clearly the salinity intrusion in the Yangtze estuary is nonlinear with respect to wind. And the map, which by the way, the graphics in the report are just beautiful, and it shows that with the multiple channels connecting the estuary, the river to the sea, there are, I think it would be obvious that depending on which direction the wind is blowing from and how strong, there are multiple paths for salinity to intrude. And so there are multiple ways that salinity can react to that. And so that's what creates the nonlinearity there. But there are also many others. In the Cape Fear River, for example, McAdory 20 years ago found that deepening the channel, the navigation channel, caused the channel to become fresher on average, the exact opposite of what we would expect. A very nice case study, and I can get you that reference and other. If you contact me afterwards, I'll supply you with that reference. And then that was a numerical model study. And then in a physical model study in the Chesapeake Bay, Richards and Granite showed that there was very clearly a nonlinearity that occurred during the neap to spring cycle, in which mixing characteristics changed suddenly. There was a trigger point in which the mixing changed, and suddenly the response was very much nonlinear. And there are others. There's been very strong suggestions that San Francisco Bay responds this way, and there are others that we've seen that we suspect, of course, that there are reasons that they're nonlinear, and but have not perhaps not explored them in enough depth to examine exactly why. The other point on that same page 82 that I want to emphasize is that model results should always be interpreted carefully. And Tom was quite had a very pungent phrase that I enjoyed, and he said, "Don't let the model be a ventriloquist." and that's very true. We have to interpret them. We can't take those results and simply repeat them. Let the model speak through us and say, these are the numbers, and this is what the model says. Instead, we have to interpret them, and that leads to one of my favorite quotes. That's not as catchy as ventriloquism, but Tony Thomas, one of my mentors, said that the purpose of modeling is insight, not answers. And that's beautiful, because it ties in with Thomas' comment about specialist knowledge is required. If you get someone who's maybe very expert in numerical modeling, and you get those answers out of the numerical model, but they don't have the specialist knowledge that Tom mentioned, they don't know what it means. They don't know if it's reasonable or not, and they can wind up providing answers that in fact are quite contrary to what the real physical situation is happening. And so it takes that specialist knowledge to take the model answers and to use that to create insight and to provide judgment about what the answers ought to be. And so that's very, very important in modeling and in any application to salinity intrusion. Page 123 is one of several pages that lists a number of numerical models that are useful in this. And I'll just add that there are 3 other models in widespread use in the USA that are quite good. One is the EFEC, which is supported by the Environmental Protection Agency, ADH, that Gary Brown has had a big hand in. That's used by the Corps of Engineers and supported by them. And then FVCOM, which is a joint product of the University of Massachusetts and Woods Hole Oceanographic Institute, and it's widely used. It's a community model that is widely used and modified, as is EFDC. And so these are models that are widely used in the US, as well as some of the European models that have been mentioned. And they're good models. Every one of them is an excellent model that can be used in the hands of an experienced user as valuable tools. The report has a nice section on the Mississippi River sill, and this is a genuine success story for the Corps of Engineers. And I apologize for my old-fashioned graphics here, black and white. But here it shows the Mississippi River, and it's flowing from Baton Rouge to New Orleans to out to the Gulf at near below head of passes here in the lower right-hand corner. And the problem is that it is a salt wedge estuary, highly stratified, and the salt wedge has intruded above New Orleans at times. It's gone several, a couple of 100 kilometers upstream, and there are a number of freshwater intakes along that stretch of river beginning just below New Orleans that have been endangered or simply put out of commission by that saltwater intrusion. So when the Corps of Engineers wanted to deepen the channel, one of the schemes they came up with was that to build a temporary sill that would go in and be built during times of high flow at 103 kilometers above head of passes, which is shown down there in the bottom. And the intent was to block the saltwater intrusion. And that was modeled by Billy Johnson and some other folks in our shop at the Waterways Experiment Station, then it was called, in Vicksburg, Mississippi. And we found indeed that it would succeed in blocking the salinity intrusion. And so then some years it was constructed 3 times, but after the 1987-88 time period when it was used, we, Don Pritchard and I, gathered the data that was used, and we followed it, of course, during that time, and we gathered the data and published the paper that's cited in the document, in the report, and did an analysis of the system. And this is a cross section of the river, and the very heavy line is the bottom, and you can see it's a series of peaks and valleys, or crossings and pools. And the sill is shown on the extreme right, and then the Gulf is off 103 kilometers to the right, and the top of the sill is at 13.5 meters below the national datum, so that vessels can sail of the design depth can sail over the top of it without interference. And then during the high water flows, the water will erode that sand sill, which is just creative sand pumped from the river bottom into a broad mound, and then they will erode it and it will be gone. And sure enough, it has eroded each time it's been built. However, then in 1988, the first time we tested it, we panicked because we started sampling salt water upstream of the sill, and we thought, oh no, something's gone wrong. But after repeated sampling, we found that what was happening was there were interfacial waves propagating along the interface of the salt wedge between the salt and the fresh water that were apparently generated by storms in the Gulf of Mexico. And these interfacial waves would propagate this 100 kilometers upstream, break over the sill, and then just deposit a small amount of salt water each time the wave broke. And you can see the limit of saltwater intrusion, and I cleverly colored that little bit of red there being the extreme limit of saltwater intrusion in 1988 to show that that's as far as it got, and it remained in the deeps. And then the next freshet of fresh water that came down, it flushed all of that out, and as well as removed the sill. So it was all, as I say, all in all, a great success. It's been done 3 times, and I think it's a success story. And as Gary Brown has pointed out, this is sort of an engineering of nature type thing, because it's a minimal structure. It goes away and can be ignored except during low flow periods. And finally, that's my contact information at the bottom. If you want further information on any of those or the citation for some of those reports, that's my email at the bottom, and I'll be happy to address those questions or any others that come up. And with that, I will turn it back to Tom.
Okay, thank you, Bill and Maite, of course, for your presentation earlier. We now turn to the Q&A. We see a number of other questions coming in during the chat, so thankful for those. Initially, what we wanted to do as a working group is take the privilege of asking our external speakers the first questions. So I'd like to do that. We'll have 2 questions from the working group, and then we'll turn to the participants in the chat. So I'd like to turn my first question to Bill. Bill, you talked a bit in your presentation about having to be careful using numerical models and the need for insight and specialist knowledge, just like Tom did in his presentation on modeling. But in your career, what were the worst or the most common errors that were made by engineers studying saltwater intrusion in waterways? What sort of errors did you come across?
Good question. Probably the biggest issue that I have seen over many years in numerical modeling is the validation process. And I see very poorly validated models in the literature, in the papers that I review, in the projects that I'm asked to review. And that arises from two processes. One is that there are a great many modelers who have academic training in models, but very little practical management training guidance from their management in modeling. They know how to operate the models, but they don't understand the validation process. They don't understand that it's a process, and they've fallen into this trap of the two-step calibration validation nonsense that they think, okay, yeah, that makes it great. And so they make just really awful mistakes in trying to validate their models and then proceed immediately into testing. The other part of that that actually complicates that is bad field operations, bad field data. And Gary Brown mentioned in his presentation on field data that the need for quality control and so forth. And one of the things I've encountered repeatedly in my career is terrible, not just error. Everybody knows there are errors in field data, but terrible mistakes. People who claim they were sampling surface, or claim they were sampling bottom salinities when in fact their meter were sitting at the surface and that sort of thing. And so I finally had to make a rule in my organization that if it was all possible, the engineer doing the modeling had to be on site during the field data collection so that she or he could witness firsthand what could go wrong and what had gone wrong, and be able to take that into account when they enter the validation. So those two things, inexperienced modelers and bad field data led up to bad validation and bad conclusions based on field data.
Thanks, Bill. And Mainte, in your presentation, you talk about operational use of models. Does that ask for any different or extra care or different types of validation of those compared with other models which are used in other types of projects? Or what's different about doing it for operational water management than for other types of projects?
That actually depends a bit on the decision problem that you have at hand, right? So in operational sense, in fact, on every level, the decision is about risks. And if you want to know the impact of a wrong decision, you have to be careful and you have to be critical on what knowledge do I need and what information do I need from a prediction or a model that's critical to reduce that risk. So that's a starting point to find out where and on what scale level you need some data and additional data, maybe even to validate a model. So sometimes the devil is in the details. If you see a little flux term somewhere is really influencing the state of your system, you need to be very careful that you have this flux term in your observational network and in your forecasting system. But if it's some background term that doesn't really matter for the decision at hand, you can accept some bias, right, in your model. So it's dependent on the application, what demands you put on your model. Sometimes you can have right for the wrong reasons if it's empirically well validated. But I agree with Bill, actually. It's not, and with Tom, it's not like a box of magic, right? It shouldn't be a black box. You should be able to know what is the risk involved for this decision. And there you put your effort on, or where to validate.
Yeah, okay, thanks. I think we're all agreed that it's not just pressing the buttons on a model,
Exactly.
but we really do need to consult an expert.
And look to your chain of cause and effect within your system. Where is it a critical weak link in your chain? That's probably where the high risks are.
Okay. Thank you both for your contributions, and stay with us obviously now for the Q&A. We'll also have the other presenters and perhaps other members of the working group available to answer the questions. If I turn to the questions, I'm not necessarily going to address them in the order that they came in the chat, because I'll try and group them somehow. But I will start with the question from Steven Kaptein, because he was the first one in. His question was, how important is, on average, the salt intrusion due to ship displacement with respect to the salt intrusion due to density currents in ship locks? Now, we do say something about this in the report, and as you can imagine, it depends on the relative dimensions of everything. But in general, we say in the report that the lock exchange is often that is to say, the density currents are often the dominant source of salt intrusion through locks. That's our experience. But of course, it does the net effect of everything should be accounted for, because it can be the ship displacements. Obviously, if the ships take up a large part of the lock chamber, there's less volume of water in the lock chamber to intrude once you open the gate, right? So, and there doesn't seem to be any reason why you can't take into account those volumes. You can take them into account. So do so. Slightly related to that is a question from Carsten Torrens. How important is the mixing due to ship propellers in low mixing areas, canals or stratified rivers? So the ships sailing through a canal and their propellers adding to the mixing. So Bill McAnally, I think you had an example that you wanted to mention of where that is an issue. So can you talk to that?
Sure. Well, we saw that ship mixing due to propellers was a big issue in Mobile Bay. We had a physical model of the estuary. We couldn't get the Salinity intrusion out of the channel, or the Salinity spill out of the channel, right until we installed tiny little vessels, miniature vessels, going up and down the channel with their propellers turning, and we had to tune that. As you can imagine, that was quite an artificial, tedious process to get that right. Then when we did the numerical model, we had to introduce something special in terms of additional mixing in the channel to reproduce that same thing. In Houston Ship Channel, just down the Gulf Coast a little ways, the ship propeller mixing and the displacement of the ship hull pushes salt water out of the channel and into the overbank, and we documented that very thoroughly with field data, and had to replicate that in the numerical model. And so there are a number of cases like that where there's low mixing from tides and other winds and so forth, that where vessels do indeed cause a great share of the mixing.
Okay, and Mijnte, I suppose in the Netherlands, with all of its closed off reservoirs and canals, quite a lot of areas which are low mixing areas, been cut off from the tides. Are there also examples there?
Yep, definitely. At least we suspect, for example, in the Amsterdam port area, so the North Sea Channel and the connecting channels, there is some striking weekday, weekend day sort of pattern visible. We're not sure yet, right? But it could be attributed to the effects of shipping that's more intense in the weekdays than the weekends. So this is just a clear suggestion, at least, that there is quite some influence of shipping motion and propellers to the vertical mixing.
Yeah, and in some of these canals where there isn't much through flow, you've only really got a couple of mechanisms for mixing if you see it, and that is either the ships or the wind if it's there. So
yeah, but the wind doesn't care about weekends, so just for this stage we become suspicious.
No, but I think there is one example in the report where we have a graphic from Rijkswaterstaat to show a freshwater bubble at the Krekerak locks, and in that canal it's fully vertically mixed, and yet that canal is running north south, and the prevailing wind is west east, and so we sort of thought, I think we mentioned it in the report, that the almost the only source of mixing in that canal that could possibly be causing the vertically mixed profile is the shipping. So I think we also have
that's another case
in the canal of this being the most important aspect of mixing in that location.
Yeah, because it's sheltered, it's even more obvious. Yeah.
And since we're talking about wind, let's get to the question of Thomas Wakeman. Did the report discuss contributions to intrusions from wind? But I suppose this is also related to open estuaries. I suppose this issue. I think Bill mentioned it shortly in his presentation that there's an example from the Yangtze estuary, but Frank, you talked about the mechanisms chapter, and wind is one of the mechanisms. Yes.
Yes, we discussed that. I think wind, the main effect is that wind stress is changing the horizontal circulation, and by that you have different water masses which can enter the estuary, for example. So the physical mechanism is the wind stress on the one hand, and on the other hand, wind speed that might increase the evaporation, and with increased evaporation you have higher salinity water outside of the estuary, and that can then intrude into the estuary. These are two mechanisms which play a big role, and especially in the Asian region, the South China Sea, for example, which Bill has shown just before.
Yeah, so there are also some general discussions about general principles of what effect wind has. The example from the ANCSI also shows that the geometry, if you like, of your estuary can have strange examples, but even in an estuary that is not quite so complex, wind can have an effect, and those are discussed in the report. Okay, thanks. Moving on to another question. The next question here is from Sebastian Iglesias. He says he's already been using the guideline, so he's been busy since July. Thanks for reading it, Sebastian. His question is about nature-based solutions. He says the guideline mentions that measures for salt intrusion are not commonly designed or implemented according to nature-based principles, working with nature, for instance. So his question is, what specific considerations come to mind if you have to assess the impact and implement nature-based solutions of salt intrusion? If I can start at this, there is a separate PIANC report on nature-based solutions in navigation infrastructure, and I think that Bill and Gary mentioned that the Mississippi seal is actually quite a good example of where, before that term became a buzz term, nature-based solutions, that they were already working a bit along those lines in the Mississippi. Gary, can you say something to this question?
Yes, I think that the report, the way we lay out things in the report are more general in terms of the when we talk about the processes and the mechanisms that the mitigation, the mechanisms whereby the mitigation measures work. Those are all process-based. So the nature-based solution connection to that would be that the nature-based solutions still have to address the same processes and address the same mechanisms to mitigate it, but they instead of using necessarily hardened or permanent or intrusive infrastructure, they use natural means, natural resources, or maybe leveraging other resources like sediment sources and things like that. The Mississippi River salt wedge is a very good example of that, because again, all that is basically dredging sediment out of the river, redistributing it to create an artificial crossing to mitigate the intrusion, and then when the river rises, it just erodes back into the system. So that's a good example of that. One of the other examples that we discussed in the report are just basically small tidal estuaries or single inlet tidal estuaries, mitigating the tide range by constricting an inlet. When we looked at that, one of the examples of that's put in there is Salt Bayou, which is in coastal Texas, and that was actually done in conjunction with larval fish modeling, because there's a lot of larval fish recruitment there, and we designed those specifically to minimize impacts on larval fish recruitment. So I think a lot of the engineering with nature issues will have to do with recognizing that salinity mitigation can't be done in the absence of consideration of these things, or specifically consideration of also with sediment transport. One thing I'll also mention, and I think we talked, I don't want to jump on, we were going to talk about sea level rise as well, but this has to do with that in terms of mitigation. One of the things about sea level rise is that in terms of assessing impacts on salinity, it's formally an uncertainty analysis, because we have pretty broad range of uncertainty about what the rise will be, and that can have dramatic impacts on predictions of salinity impacts, and really it can have to the point where for certain sea level rise scenarios, a project may have significant impacts because of the changes it could make. But for higher sea level rise scenarios, you may find that the entire estuary is transformed. So the project, ironically, a project may have very little impact with very high sea level rise, because the sea level, the salinity has already changed so much just by virtue of the sea level rise. So there's a lot of dynamic effects there. And I think we have to, the challenge is to be resilient to the effects of sea level rise in an environment where the actual value that we have is significantly uncertain. And that becomes a real challenge in a coastal environment.
Okay, thanks. Gary, I think Sebastian also had a second question, which I think is also partially addressed here by Gary. His question was, is the guideline still applicable for the implementation of nature-based solutions or other aspects that we would add? And I think Gary's answer is yes, it's applicable, because a lot of our advice is pretty general, and do your modeling right, and do your measurements right, and look at try and understand the physical processes, and exactly the same sort of advice we'd give if you're considering a nature-based solution. I think if I can maybe add to it and say that Sebastian may be right, that if you look in the mitigations chapter, it's a big chapter and there are a lot of examples, but a lot of the examples involve some sort of a hard infrastructure, which would maybe not conform to nature-based principles. So lots of the examples that we can use from the past, you wouldn't include under those. So that's maybe correct to say that even though we present it as, oh, we've got this huge list of mitigation measures, lots of them maybe don't conform to modern ideas about what is acceptable in an estuary. Having said that, I remember writing this part of the report and saying the Netherlands closed off their delta and quite harshly with a big storm surge barrier and dams, and these days we may not do that quite so readily because of the effect on nature. And as soon as I'd read that, I then went to a conference in Cardiff where they just closed off their bay with a big dam and concrete. So I mean, people are still doing that, right? So so in that sense, it's still relevant for today, because sometimes a society will make the judgment that they still, for other reasons, maybe freshwater availability or flood safety, want to make that choice to close off an estuary. Okay, moving on to another question. We've got one from Jeroen Adema. A number of mitigation measures were mentioned in order to reduce saltwater intrusion from locks. Is there a general rule of which is most effective? It's obviously we do talk about. We had to give a piece of advice at the end of the mitigation chapter about which ones are most appropriate for different situations. That's in the report. So I would suggest reading that carefully. And it's obviously very dependent on the situation. It is very dependent on the situation. It's difficult to give a general rule. I think in the past and currently, mostly people use flushing of fresh water, flush the canal and the lock with fresh water. That's the most often used method, and it's relatively cheap if you have the fresh water. But as Mainte also said in his presentation, and climate change is a big function in this. In the future, you may expect that becomes under stress, and then you need other measures when the droughts come. So probably flushing is the most cost effective, because the water flows downstream under gravity, and it doesn't cost you too much to get it to do that. But yeah, it's limited when the fresh water becomes scarce. Okay, move on to another question. So this is from Thomas Kluiver. Does the PIANC report include any discussion on an outlook to the future? He's interested to hear from the presenters their perspective on the potential increase in saltwater intrusion from sea level rise. And whether there are any tipping points to consider. So Gary, you've mentioned sea level rise, that it's not doesn't always have a big effect on your navigation project or on your salt intrusion mitigation project. But what are the tipping points in implementing mitigation strategies? Can you say something to that, maybe, or anyone else that wants to jump in on this?
Yes, I could. That's a good question, because one of the things I found in a lot of work is there's an irony to looking at salinity intrusion from sea level rise, which is, so for example, if you're proposing a project and you're looking at mitigation, and I kind of referred to this, but it's in some cases for the higher sea level rise scenarios, what you find is that you can build the project without any mitigation, because the entire estuary is lost. In other words, the reason you're mitigating is because you recognize that you're disturbing an estuarine condition or maybe oyster habitat or something like that. So the project's going to take away some of that, so you have to mitigate for that. But under the higher sea level rise scenarios, you find that the entire estuary is no longer appropriate habitat for those things. So there's, what I mean by that is an irony. There's a tendency to think that the higher sea level rise scenarios are going to require the most mitigation action, and sometimes you're saying we've lost this project or we've lost this resource at this point. And so
when you've got when you've still got something to protect, then you've got to work hard with mitigation. But if the external factors are so big that there's no chance of protecting it, then that's your tipping point.
That's right.
That is
exactly.
a shame, just because you've got no hope. That's not the moment we want to end the webinar on, but no, but it can be a conclusion. Yeah.
But again, you have to recognize you just have to be resilient to that, because it's also possible if we don't get that kind of sea level rise, now you have a situation where you do have to mitigate, and you have to. So it doesn't mean that it just goes away, or lower sea level rise, I should say.
Yeah. Okay, I think we've got time for one more question, which I think I've done it out of order. I missed it in the chat. This one's specifically for Mainte, also from Sebastian again. So specifically for Mainte, thanks for the presentation, Mainte. Could you elaborate a bit more on the way in which multiple objectives are handled on a regional scale? For instance, the objectives of freshwater supply and waterborne operations are commonly colliding, right? So the shipping and freshwater supply.
Yeah.
What is the information that decision makers require to handle these trade-offs for colliding interests?
In the end, well, it reflects a little bit to the risks and impacts that I already discussed in a moment. In the end, it all is about impact, right? So impact to different functions. And so what we do in the Netherlands, actually, we also have models on top of the physical models that quantify, or at least objectify, something of the impact to environment, to shipping, to drinking water. And this is input into a decision-taking process that's also political, of course, and also setting up these lines of reasoning that we do in this smart water management. It's fed with these kind of still causal relationships, but in the end, it's also a negotiation issue. And that's what we're in Holland are famous for. It's poldering. It's what we call poldering, finding the compromise between certain values. And that's hard to fit into a model, but the models and the objective information give an input to that process. And it's, in the end, it's pinned down into objective criteria, right? In the end, you say, okay, if this happens at that level of salt concentration, under these circumstances, we do that. And if circumstances are different, we do such. So in the end, it's all the fuzzy stuff is being put back into firm lines of reasoning that we have consensus about. I hope this is the answer to the question, actually.
Yeah, I think I would also recommend Sebastian to look at some of the other PIANC reports, which I think are referenced in the report, because they can more focus on the process of weighing up, trading off different stakeholders in a navigation project. In our report, we really concentrate on getting on how to get the answers about salt correct, and not necessarily as an input to some sort of stakeholder analysis.
No,
I think other PIANC reports give more insight into how to do the stakeholder trade-off. Okay, thanks very much for all your questions. We've almost come to the end. I wanted to give the floor for the last 5 minutes to PIANC themselves, and specifically Philippe Rigaud, part of InCom, who's the person. InCom is the Committee for Inland Navigation in PIANC, which gave us the assignment to make this report. So he is the person that we sent the report to when we are finished, and say, I hope this is what you meant, Philippe, and InCom. So he's going to tell you a bit more about InCom. Over to you, Philippe.
Yes, I'm here, Tom. Thank you very much. So hello to everybody, to the working group member, but especially also to all the participants. So I'm very happy to see that there is a so large participation today. Once more, I want to thank the working group and his chairman for a very efficient job and a very, I say, high-level report that has been issued. So my purpose is, okay, not to make publicity, but anyway, I would like to promote a little bit PIANC, especially for the person who are not fully aware of what are the different commissions. So as Tom said, this report has been promoted and supported by InCom, which is the Inland Navigation Commission, but PIANC has other commissions more on maritime transportation, also recreation, and a fourth one more targeting the general environmental consideration related to navigation. But come back to InCom. I would like to present you, without take too much of your time, few working groups that has been published that are currently on process, I would say, and maybe you may find already today some interest for some of these reports. Yes, my system is working. I can change the slide. So obviously today it was the time for the webinar of this working group on saltwater intrusion. I personally has been involved in many projects in the past, like Panama, but also in France. And I realized that for locks, inland locks, I would say, these problems of saltwater intrusion can be very important. And I want to a little bit develop the reply of Tom to Mr. Andema when he was asking about the best or the most effective solution, and also the most cost-effective solution. So personally, I would not recommend any most cost-effective, because cost-effective is very case-dependent. But I would say that scientifically, at least is my point of view, we can solve the problems. And we can solve the problem technically. So it means without having any sort of intrusion and without losing, my word is missing, releasing fresh water. Because if you design a system which is a little bit more general, it's completely possible to remove, to replace, to exchange, depending on the word that you want to use, but the salt water, and to avoid any mixing of the fresh water. And you can even repump the fresh water to avoid to lose it. And if you combine that with other green approach, like floating PV panels or wind energy, you can have something that does not create any effect on the, I would say, on the CO2 production and so on in the field of decarbonization. So I think the solution is there, but can we pay that one? I don't know. That's of course another issue, but that's my personal view. So I will not interfere too much with the expert of the working group, and I will continue my presentation. So here you have 4 working groups that released their report in 2020. So the first one and you can see the last one, there are 2 working groups who study the classification of waterways. The 179 is for the European classification of inland waterway, and the 201 concern the South American inland waterways. So these 2 reports propose new classification or new methodology to make some classification. And then you have in the middle the 189 and the 191, who are more technical working group, as this one on saltwater intrusion. One concern the fatigue of hydraulic structures, which is a key issue for for the sizing, for the design of the structure, but also for the operation and the maintenance, and so it means also for the life cost of this structure. Composite materials is probably not, I say, a common technology, but that report and the webinar that was organized show how much it could be attractive in the future to think about composite materials instead of composite hydraulic structure, sorry, instead of steel hydraulic structure. Okay, do you listen to me again? Okay, I can continue.
Yeah, we can hear you again, Philippe. Yeah.
Yes, something happens, but okay, now it's going back. This report published this year, it may be complementary of this report. It's related to the small hydropower plant in Waterway. Okay, so we are not talking in the report about the big dams to store water. It's really the small hydropower plant that we can put in the waterways, in the navigation waterways. Now, few working groups started their job in 2020 or 2021. One very important, I think, is thinking about the decarbonization of the inland waterway. How can we do that, especially with regard to the inland waterway infrastructures? So it's not too late to join these two working groups also. So the 236 is about the sustainable management of the navigability of free flow river. So of course, all the river in the world, especially in South America or in Asia, are not what I would call typically a canalized river. They remain almost free flow rivers. And how can we manage to keep the navigability on a sustainable way? That's the challenge that will be discussed by that working group. So not too late to join it. Contact me if you are having interest. And the next one, bottleneck and best practices for transport of container of inland waterway. The container transportation is not something new, but since the last 10 years, many change occurs. So you see that these two working groups started few months ago, so still time to jump on the train. Also possible to join on the train on the handling accident and calamities in navigation in hydraulic structure. So that report, that working group would like to propose some methodology how to manage the accident, and of course from the lesson learned to try to minimize in the future such kind of accident. And we have, I would say, in our luggage, a new working group that we would like to launch soon, probably early next year. It concerns the use of the inland waterway. Typically, we have that in France, in many cities, of course, in the Netherlands, where in the large cities, all the banks are used for permanent floating houses. And that is, of course, a problem of the management of the waterways. So we would like to, in some way, collect a little bit the lesson learned from all the country who has this phenomena, which is growing. And I will finish by an invitation to all of you to join. Why not to travel to China? Or there is a small mistake in my slide. It's not Smart River 23, it's Smart River 22. It still is 22. And that Smart River conference will be organized remotely and in presential. So a person may go there, present their paper as usual, but due to the COVID, PIANC, of course, realized that obviously a remote presentation will be welcome. So we are, I think, 10th of December. The call of paper officially is almost finished these days, but I have been informed that our Chinese colleagues from the organization committee will welcome a paper that arrived a little bit late as early January, but not much later. So please take a few minutes to send an abstract in right now before Christmas or just after New Year's. So that close my short talk. And again, congratulations to the working group and thanks to attending this meeting. I'm looking to see you at the next PIANC, one of the next PIANC working group. Thank you and goodbye.
Thank you, Philippe, for your compliments on to the working group and to the report. I'd also like to say that I found the experience of being in a working group very rewarding, so I can recommend it to other people. It's a little bit sorry that that it's over, but with things like this webinar and future conferences, we'll have the chance to continue the collaboration that we've started. Thanks to all the participants of the webinar today and everyone at the working group. I hope to see you all again at another PIANC event or Congress. Thank you. Bye-bye.